on this computer. Great. Okay, so we're still talking about chapter 2 of the Bermuda's textbook. Last time we talked about two milestones in cognitive science. One is about building a computer that can carry on conversations with a human, and the question of like what's important to making a computer have the ability to communicate with somebody, understanding the meanings of the terms, to use language meaningfully instead of just parroting back sounds. Then we also talked about these experiments on mental rotation in working memory of objects and how that seems to have an analog format of representation instead of digital. The thing that we didn't get to in this chapter is David Marr and his work on vision. So he publishes a book. He dies in like 1982. He died very young, but he had this book on vision, which was very influential on cognitive science, both because of the model of vision that he put out, but also about the way he went about building his model. And that's actually what had the biggest impact on cognitive science. So I want to talk about that. And first, let me get to that in a kind of roundabout way. Let me talk about a distinction I didn't make in the first class, which is the distinction between the mind and the brain. The brain is a physical object. It's a squishy, heavy thing that's made up of squishy matter in the skull, right? It has a weight. It's made up of particular material. It has an electrical charge. You can see, you know, it's all the physical stuff. Now, the brain is related to the mind, right? It somehow generates the mind, right? Or if our mind is a ghost, that's the place that the ghost talks to the rest of the body. That's the cockpit for the ghost, right? But probably what's really the case is that the brain is like a movie projector, and it produces the mind, right? So the mind is something over and above the brain, but you know, the mind is beliefs and desires and decisions and our knowledge of chess and our knowledge of English and where conscious, you know, where conscious experiences, you know, if you carved open the skull and looked for the conscious experience of red, you're not going to find red and green and you know these conscious. You won't, you know, you'll find neurons firing, but you won't find pain, right? So like the brain is generating the mind, but the mind seems to be something over and above the brain, just like you know the game of chess is something over and above the board. Right? I can lose a pawn. I can put a penny where the pawn was, and I go, that's the pawn, and I can play, right? It doesn't really matter what the physical makeup is. The game is something more than just the physical pieces, but it maybe depends on the physical pieces, right? Maybe I need the board. But great. So the mind is what we study, you know, when we're interested in behaviors and knowledge and understanding and feelings and beliefs and desires and what it is to be me. And they all depend on something physical. It seems like they depend on the brain, right? And the brain is just the name for the physical object. So great. Now, if we're interested in this thing, the mind, you might think the way to understand the mind is just to study the brain. Let's just study the physical object, right? That's the thing it depends on. The brain determines what happens in the mind. The brain is the projector that displays the movie, so let's just study the projector. And we're going to talk today about why that's not how cognitive science proceeds and why that's probably not the best way to understand the mind. It actually kind of connects up to a broader view that lots of people have about science. Lots of people think that physics is somehow the only true science or the only one you need to know, right? If we were God, if we had perfect knowledge, we would only need physics because everything is made up of atoms or particles. And if we could know how particles move around, we wouldn't need chemistry. We wouldn't need biology. We wouldn't need sociology and psychology. We wouldn't need economics because ultimately we would know how all the particles are moving. And that's really all we need to know, right? Because we're all made of particles, so that's the only science you need. We can call this the atoms in the void view, which is the universe really is just atoms or particles and empty space, and you just need a science that tells you about how those particles move around in empty space, and that's a full description of the universe. That's a full science. That's not how most philosophers think the world works or how knowledge works or how science works. Instead, the idea is You think of the world as layers of a cake, all built upon the base layer, right? So physics is the base layer, understanding particle, everything, sure, sociology, psychology, chemistry, none of those things, all the things that those fields study wouldn't exist if there weren't particles, if there wasn't a physical basic layer. But that doesn't tell you the whole story. You have to understand the laws of chemistry, the laws of biology, the sorts of objects which these other fields study. You need to understand the world at different levels of abstraction or stepping back. Let me give you an example to illustrate why maybe studying the universe at the most fine-grained detail doesn't give you the full picture. So let's talk about Sophie the pigeon. So Sophie the pigeon, say we've trained Sophie the pigeon to peck at red things. Every time I show her a red thing, if she pecks at it, I give her a treat, right? I give her some food. If she pecks, so at first I give her a green thing, a red thing, a white thing, and she's just pecking at random. She accidentally pecks the red thing, I give her a treat. She continues pecking at random things. She accidentally pecks the red thing, I give her a treat. At some point, I build up peck at red things, and I'm swapping out the shade of red I'm training her for, right? So eventually, I train her up to peck at red things. And on one occasion today, let's say, I put a little swatch of crimson in front of her, and she pecks at it, right? What's the explanation? Why did she peck at it? You could say two answers here, depending on how detailed of an explanation you're going to give. You could say she pecked at it because it was crimson, which is a particular shade of red. Or you could say she pecked at it because it's red. What's the appropriate explanation? What's the better explanation to give? The really detailed one or the kind of broader one? The example here, Sophie the pigeon, is supposed to illustrate the way in which the broader explanation is sometimes the better one, right? The reason she pecked at it is that it was red. Had it been a different shade, she still would have pecked at it, right? She was trained to peck at red, not a particular shade, right? It doesn't matter what the particular shade is. So sometimes the broader explanation is actually the better one and explains what's happening instead of the super detailed one. So similarly with physics, like think about physics and chemistry, sometimes what happens does depend on the exact fine details. This particle bounced into this particle and bounced into this particle, and now we got this result. And I have to know the exact physics. But sometimes, sure, the chemistry depends on the detailed particles and what they're doing. But really, the explanation is the broader phenomenon of how the molecules, how the combinations of these particles and how they're bonded together and how those things are interacting. So sometimes the right explanation is, why did this happen? Because it's gold, instead of the exact explanation of what's going on with the particles. So similarly, the idea here is when you want to understand the universe, it's understanding it at multiple levels, right? I need to understand it with physics. I need to understand it with chemistry. I need to understand it with biology. I need to understand it with sociology. I need to understand it with economics, right? And these are broader and broader levels of looking at the world, which, yes, it's all made up of particles, just like red as a group. Every time red occurs, it's a particular shade of red. But sometimes the particular shade of red isn't the right level of explanation, isn't the right story to tell to understand what's happening. And sometimes physics is not the right explanation. Sometimes it's psychology, sometimes it's chemistry, sometimes it's sociology, sometimes it's history or evolution. Great. So where does cognitive science fall on this, cake, this layered cake of reality, and like which layer of reality is cognitive science studying? Actually, it's not any of these. Because the motivating idea behind cognitive science is I plopped a particular object in the middle of the room and I said, let's study that, the mind. And the mind is something that is made up of neurons and atoms, so we need to understand it on the very most basic level. It's got chemistry, we want to understand it on that level. It's got a biology, we want to understand it on that level. It's got a evolutionary story, we want to understand it on that level. We want to understand it on the psychology. So the idea behind cognitive science, its relationship to what it studies in the other sciences is a little weird, because it's not the relationship of like physics to chemistry to bio. Instead, it's a particular thing, and it wants to understand it on all of the levels and how those levels interact and how one level might help us understand a different level, right? So I want to understand how vision works. What is the evolutionary story as to why we have color vision? What role does it play in our lives? What's the chemistry? What's the biology? How does it play a role in sociology? What's the physics of the brain, right? We want to understand it on all of the different levels. That's cognitive science. I mean, you can kind of do this with other objects. Suppose I wanted to understand Minecraft, the video game, at all the levels, right? Then I'm going to study the computer and the physics and of all of the bits being stored in memory. But it seems like I don't really understand Minecraft if all I've done is study a computer, like the physics of a computer that's running Minecraft. I want to understand the software. I want to understand what sort of things get displayed on the screen. I want to understand why people enjoy it, what a game is. Probably the game was made certain ways to make it profitable and sell. That helps me understand what Minecraft is, right? Understanding Minecraft on all the levels would be different than understanding just the computer running it. Now, Minecraft is not a particularly interesting object in the universe. It's a particularly fun thing in the universe, but it's not a particularly interesting thing in the universe. Whereas the mind is, right? The mind is not like a rock. It's not like the moon. It's not like the earth. It's not like water. It's something that we really want to understand because, it's what we are. It's also very unique in the universe. It's the only thing we've ever discovered that has self-awareness, that seems to guide itself and make decisions about what it's going to be, right? Your cat doesn't just say, I'm going to lose weight. I'm going to put myself on a diet because I want to be a better father to my kittens, right? It doesn't make these decisions. It's not aware of itself in that way, right? Sometimes people say the mind is the universe aware of itself, right? Like there's something very special about what's going on here. And so we want to understand this phenomenon as deeply as we can. And so cognitive science is trying to understand that at all the levels. And David Marr, which is who we're talking about today, is famous for his book on vision because he did try to account for vision at all of its levels. He said, listen, he sort of, it's not David Marr philosophers have come to think of the universe as having these different levels and that the sciences are related to each other like this layered cake, for other reasons. But David Marr, is early on in this process, and it was particularly important to cognitive science because it sort of set the example for all cognitive scientists. Like, yes, that's what we're doing. That's what this field is. That's why we're coming together, because of these different layers. And he also gave a particular framework for how to think of the layers. In particular, he broke them down into three. He called them the computational level, the algorithmic level, and the level of implementation. So I'm going to talk about each of these three, but again, it's computational, algorithmic, implementation. Implementation is kind of like the physical layer. So computational level. Why? Right? I think this is like, sometimes people say philosophy deals with why questions and science deals with how questions. No, science deals with why questions. This is a why question though. Like computational level is like, you've got color vision. Why do you have color vision? What is it doing? Why do we have it? Why did it evolve? What purpose is it serving? This is going to be important to trying to understand the neuroscience because I can try figuring out why are these neurons firing? I need to start grouping up portions of the physical brain into playing particular roles because the brain evolved to have this particular portion to play a certain role in the human species life, right? For hunter-gatherers, right? My ancestors over millions of years evolved a certain part of our brain to do this certain role. Why do we have it? How does it come to have a why? How does it come to have a purpose? Well, at first it's a random mutation to tell the difference between light and dark, to tell the difference between, whether it's daylight or night, but and eventually maybe telling the difference between light patches and dark patches in my vision, and then slowly I get color, right? So these are like random mutations that detect light and then eventually light of different wavelengths. And each stage in this has some sort of advantage to the creature, right? It helps them survive longer, to thrive, to find food better, or some purpose, right? It accomplishes some goal, which means that they survive longer, They better propagate. They live longer. They're able to take care of their kids better. They're able to mate and reproduce better. And so they end up having more kids, and those kids end up having more kids, and those kids end up having more kids, and they eventually crowd out everybody who doesn't have this random mutation. So the idea is we can talk about what purpose did this part of our brain, like color vision, what purpose does this have? Why did it give an advantage to our ancestors so that more and more of our humans had that and eventually crowded out everybody who didn't have it? So the explanation for why I have it and you have color vision is that it serves some purpose for our ancestors that gave them an advantage over everybody else so that they reproduced more, and eventually the only humans left were the ones that had color vision. So great. So we want to understand why we have color vision. We also want to understand like what its inputs and outputs are, right? So the input to color vision is wavelengths of light that hit my eye, and the output is like a representation of, I guess, the colors around me. So why do I have, let me give you a different example than color vision, because I think this example is a little better for the moment. Depression, right? When people around you that you care about die, people you're familiar with, people you depend upon, people that you see all the time die, you get depressed, right? You lose, it saps your energy. You're unmotivated to do anything. You kind of want to just lie in bed. The things that inspired you, the things you were getting up excited to do today are things you're not excited to do. You just kind of want to stay at home, and you become less energetic, less excited to, less motivated. So why, again, if I want to understand depression, I do want to understand it at all the levels, right? I want to understand what happens in the brain. I want to understand what triggers it. But one of the things is why do we have it? And one prominent evolutionary explanation is the idea is, listen, when people around you that you depend upon and care about and are familiar with and love die, danger is about. Danger is afoot. You better not go adventuring by yourself or run around or go do the normal things you do. Something got them killed. Maybe it was disease. Maybe it was, maybe there's a group of bad guys around. Maybe there's a bunch of tigers out there. So let's slow you down. Let's make you avoid other people, want to be by yourself, not want to go out, right? Stay in bed for a little while maybe the danger passes, right? So understanding depression, maybe one of the steps is understanding what purpose is it playing evolutionarily, right? Why do we feel sad, and why does it have this effect of causing us to like not want to do things, want to be by ourselves? And that's sort of the computational level. What purpose does this computation have? Also, what are the inputs and outputs? So the outputs of depression is sapped energy, wanting to be by yourself, not wanting to do things. And the input is, I don't know, the missingness of somebody you are familiar with, maybe. Maybe it has to be someone you love or are happy about around. Maybe it's, particular people, mother, father, sibling that you imprint upon, right? Like it's not clear what the input is here, right? But there's somehow, some people die or go missing or leave your life, and the input of them going gone doesn't cause you to be depressed. Other people, when they go missing, you become depressed. So to understand depression on the computational level is to understand why we feel it, and also like what the triggers are, and then what depression is constituted by, what behaviors, so the sapping of energy. Same thing for color vision. What's the purpose of it? So what is the purpose of color vision? Our best guess right now is finding berries, mostly, right? So we were hunter-gatherers, mostly gatherers, and finding a bunch of berries in a bush is a lot easier if you can tell the difference between the green leaves of the bush and the red berries or the blueberries. Also telling whether they're ripe or bad, right? Bananas are ripe when they're yellow. They're underripe when they're green. If they're black and decaying, they're probably unhealthy to eat, right? So color vision helps you find, gather fruits and vegetables and also tell the difference between the ones that are good to eat and bad to eat. Probably has other purposes, seeing a tiger in the bushes, things like that. But yeah, but mostly I think mostly gathering fruits and vegetables. Great. So that's the purpose. And now the inputs. So how do you get to see these berries in the bush? You see colors, right? The input's colors. But let's talk about what color is for a minute, because I think people don't generally understand what color is. Really, color, when we say color, we mean one of three things. It's ambiguous. Like black is the absence of a, people say, color is a wavelength. And that's one way of thinking about color. It's, red is a particular wavelength of light hitting my eye. Green is a certain wavelength of color hitting my eye. But on that definition, black is no color because black is the absence of, right? So black would not be a color according to, of course, black is a color, but that's when we think about experience, right? Black is an experience I can have. Red is an experience I can have. Green is an experience I have. And it's, when I say the wavelength, a certain wavelength of light is green, it really is that it just triggers green experience, triggers red experience. Black is triggered when I have no wavelengths coming in. So there's color when we think about it as a conscious experience. There's color when we think of it as a light or a particular wavelength of light. And just to drive home the difference, you could imagine somebody who has the color experiences are inverted. So when there's no color coming in, they experience white. When all the wavelengths are coming in, they see black. When red wavelengths are coming in, they see, they have the green experience. You could have a brain that was wired so you had different experiences than what's traditional from the wavelength that's coming in. So great, those two types of ways we think about color, but actually neither of those is what our brain has evolved to try discerning, right? Our color vision doesn't really, it's trying to figure out what color the berries are. And so it wants to know the reflective, the chemical properties, the properties of the object. So another way of thinking about color is that this object is red, which just means that it reflects the red wavelengths, but absorbs the other wavelengths, right? So I want to know the color of the object, what sort of its surface reflective properties are. And I want to know its color, right? And when I say the object's color, I mean, what's its chemical makeup such that I want to know that it's of the sort of chemical makeup that bounces off red light and absorbs the other colors, or bounces off green light but absorbs the other ones, right? So that the colors that hit my eye are green, right? Because I want to know what color it is. I want to know things about it. Great. So that's what color vision is for. But here's a problem. What color vision is trying to do is tell what properties, what the reflective color of the object is, and it infer what's the input of color vision. It's the wavelengths that hit my eye. The problem is the wavelength that hits my eye is not, it's almost never the reflective color of the object. Why is that? Because the wavelength that hits my eye is the combination of two things: the reflective property of the object and the lighting conditions, right? What is a white surface going to look like under a blue light? It's going to look blue. What is a green surface, a yellow surface going to look like under a blue light? It's going to look green, right? So, I mean, what is a red surface going to look like under a shadow? It's going to look like a very dark red. Under a white light, it will look like a very bright red, right? So the wavelength that hits my eye is a combination of two things: the reflective color, right? The reflective properties of the object, and the illuminating conditions, right? The background lighting. And somehow, from what hits my eye, I need to figure out what the reflective property of the object is. So what's interesting here is our brain is doing something. It doesn't have enough information because it's trying to solve for an equation it doesn't have enough information for. Suppose I ask you, A times B equals 48. Solve for B. You can't do it, right? Because there's lots of things B could be that produce, A and B could be that produce 48. I don't have enough information to solve for B. Similarly, I'm experiencing green. That's a product of the reflective quality of the object and the lighting condition. Solve for the thing I'm interested in knowing, the reflective quality of the object. I can't because I don't know I need to know the lighting. So somehow our brain is processing more than just the light that hits our eye from the object. It also has a whole theory or way of processing background lighting conditions to determine what it shows us in conscious experience. I'm going to show you guys something now. A lot of you will be familiar with this. Maybe some can even guess what I'm about to show you. So I'm sharing my screen. Could you type into chat what color dress you see? I've got someone saying blue, 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 white and gold, blue, blue and black, blue, blue and black, blue and black, white and gold, white and yellow. Yeah. So, I mean, the first time, I mean, some of you are familiar with this phenomenon because this was a couple of years ago. I remember I was blown away when this happened because I saw this and I was like, that's obviously blue and black. And I asked the person next to me, what color do you see? And they said white and gold. And I'm like, are you fucking with me? Like, what are you talking about? This is clearly blue and black. So humans, there seems to be a pretty big divide like between us, whether we see this as blue and black or white and gold. The wavelength that's hitting our eyes for all of us is blue and black. But what's happening is you see how you can kind of see this white light in the background, like you can see a light shining on the side of this image. Some of us are interpreting that as just a white light bouncing off of a blue and black. So just treat this like the same wavelength that's hitting your eye. For other people, oh, no, that's making something that's white and gold look blue and black. So what reports to your consciousness is white and gold, right? So what gets to our consciousness is not just the wavelength that comes off the object, but also it processes it with information about the background, and it tries to decide what color it really is, and that's what it shows to us. And now we're starting to get away from just what the inputs and the outputs are and why we have color vision. And we're starting to talk about exactly algorithmically, what's the process of how it works, right? And it seems like the way our color vision works is it takes the wavelength that bounces off the object, and it also takes the wavelength of the things surrounding it, maybe other things, maybe our belief about where we are, maybe our feelings about whether we're underwater, maybe air pressure. I mean, it's not quite clear what all goes into trying to decide what color the object really is depending on the lighting, right? So it's more than just the wavelength that comes off the object. It also, our processing before our conscious experience of the color takes in the wavelength, but then somehow has this additional part of the process where it tries to guess at how the lighting conditions are affecting the color of the object. I mean, obviously we need to do this because I need to track an object, even though shadows are getting cast on it, even though it's under different lighting conditions. I can look at a wall. I know that that wall is blue, but also there's shadows cast on it. And if I turn the lights off, I don't think, oh no, oh my God, it's a black wall now, right? No, I know it's a blue wall. My brain is always trying to keep track of the colors things really are, and not just the way they appear to me. Let me give you another example of my screen sharing is paused. Okay, let me show you some other optical illusions real quick. Here's how the dress actually looks. Let me show you that. If you didn't have weird lighting conditions. So everybody should, I think, see blue and black now, right? This is the actual dress. So now it should just look blue and black. So it's only when you've got that weird photo with the lighting on the side that it starts to look white and gold. And that's just because of the way color vision actually processes information. And it's understandable if, color vision is meant to help us pick out berries, because the berries will look different depending on their lighting conditions, and our brain is trying to interpret that. For this very primitive human too, right? The human needs its eyes, its visual system to do all the processing for it, because it's a dumb hunter, right? Gatherer, not some sophisticated person who can reason about what they're seeing and what color the object actually is. Let me show you something else too then. Let me show you another optical illusion. Here's another one. I'm not quite sure if I can explain why this one happens, but these are two lines which are the same length, but they of course appear different lengths. So this is another like what's going wrong about how our algorithm for processing the length of lines, why is it treat these as different lengths when they are actually the same length? And why was that probably useful? I mean, it's not useful here, but like for how our ancestors, like the purpose of telling telling for our ancestors, telling the different lengths of lines works in a certain way that was very advantageous for them as hunter-gatherers. In this case, it goes wrong, but it must have been the way it works must be very useful for them, and the only reason they didn't have to tell, like this wasn't important for them, telling the difference between lines like this. But whatever they were doing, the most useful way of going about it must go wrong in this case, which is why we have this optical illusion. Let me give one more case, because this is one we're going to talk more about later. This is the duck rabbit. So, you don't, I mean, maybe you just see this as a bunch of lines, but if you look at it and you think about duck, think of it as a duck, and as the two little lines going off to the left is its bill, right? It starts to look like a duck to you. And then, of course, I could also think of it as a rabbit, right? Think about it with the word rabbit in mind, with the dot as the eye and the mouth on the right, and the two lines coming off as its ears. And now it looks like a rabbit. So now my thinking of how I think about it and what I know is actually causing it to look different to me. And that's peculiar. Because earlier, when I told you that that dress was actually blue and black, your knowledge of that didn't change the way it looked for you if you saw it as white and gold. Same thing with those two lines. When I told you they were the same length, they still look like different lengths. But here, when I think about it when I'm thinking, oh, it's a duck, or I think it's a rabbit, it actually changes the way it looks. So why is it that sometimes my thinking about it as a certain, like my knowledge can penetrate, we call this cognitive penetration, penetrate my vision and change how it looks, but in other cases it doesn't. In fact, I actually don't think that that's what's going on here. I think when I think about it as a duck, I actually visually with my eye trace it differently. And that triggers my basic system to think of it, think of it as a duck instead of whereas when I think of it as a rabbit, my eyes trace it a different. So it's unclear what's going on in this case. Some people think the fact that I think of it as a rabbit is changing the way it looks. I think when I think of it as a rabbit, it's changing the way my eyes are tracing it, which causes it to look different. But again, this is a kind of an interesting puzzle here, why some optical illusions are persistent. And even when you know they're an illusion, they stick. They still look the wrong, right? Why does, when you know the dress is blue and black, it still looks white and gold? Why do you, when you know those lines are the same, it still looks different lengths? In this case, if I think of it as a duck or a rabbit, it seems like I can change how it looks. So there's a question as to why that happens in this case. In any case, the answers to all of these optical illusion questions is questions about at the algorithmic level, right? We have this color vision. Why does color vision exist? What's its inputs? What's its outputs? Why did it evolve? And then at the algorithmic level, how does it work? How does it accomplish that goal? How does it go from those inputs to those outputs? And then once you, and looking at cases where it goes wrong, like optical illusions, can help us understand exactly the algorithm, the process it goes through, how it combines information. Does it just go from bottom up, or does it go top down too? So it builds a little bit of a model, and then it asks, and then it tries to take a guess at what color it is, and then it brings that information down and revise, or does it just go from bottom to top, right? Is it a back and forth process or not? I mean, those are all questions about how it works. There's lots of ways, lots of procedures, lots of algorithms lots of ways in which you could program to go from the inputs to the outputs. The question is exactly which program does our mind use? That's the algorithmic level. Great. And then lastly, there's what we might call the implementation level. How do I implement this algorithm? How do I build a system, that serves this purpose, that takes inputs to outputs, using this process into a physical object? So then I'm interested in physically, how is this? There's lots of ways I can take a process and build it into a physical object, right? Just think about think about the different ways you could follow Google Maps, right? You could look at the map, and you're following on your phone or Apple Maps, right? And you look at them and it has you located and it has you on the map and it's pointing you in a direction and you can see the route and it tracks you as you move down the route, right? That's one way of following a map to get to a destination. Another way is, you can click and it just shows you directions, and 500 meters turn left, and 300 meters turn right at this street, and 2 miles, after 2 miles, turn left again at this street, right? That's not using the map. It's a different way of accomplishing the same goal, right? So there's like different ways of both using, the algorithm can work differently. Also, physically, you can program, it can be implemented in the physical neural architecture in different ways. And we want to understand all 3 of these levels. And in fact, it's not like you have to start with one and work your way down, although I think Marr tends to think you should start with the computational level, like what is the system and how do we understand it? But like really, we could start at any of these levels. And in fact, our knowledge of one, even the neural level, can help us revise things on the higher levels. So suppose I have this model of color vision and what its purpose is, and then I come up with the algorithm that I think it follows, given a bunch of optical illusions and other research. And then I look at the brain, and there's like no way I can find anything in the brain that works that way. And then I go, crap. All right, well, I guess I was wrong. I need to revise something at the computational level or the algorithmic level, right? So it's not like you work top to bottom. You really work in both directions at the whole time, right? So cognitive science is going to be made up of, I don't know, evolutionary anthropologists, evolutionary psychologists, philosophers working at the computational level, philosophers and psychologists working at the algorithmic level, neurobiologists at the lower level, and they're all talking to each other, and they all have maybe a little bit of knowledge of each other's work. Maybe there's somebody who's a genius and knows all the levels and is equally a psychologist and a philosopher and a neurobiologist. They have a PhD in 10 different fields, and they can do all of these equally well. But for most of us, you've got your home base and you're trying to keep up to date a little bit on the other ones and talk to your colleagues so that we can build a model of the mind that's jumping from all of the levels and drawing upon all of the levels at once. I mean, you might end up with competing theories where it works really well on the computational level, but very poorly on the neural level, whereas another theory works very well on the neural level, but totally terribly on the other ones, right? So, you might end up with kind of conflicts in how to understand the mind because we can't work out like a unified theory that handles some phenomenon equally well on all the levels. Great. So let me talk about the actual chapter, which talks about Marr's theory of vision. And in particular, it talks about how he thinks we go from a 2D model to a 3D model. So he says, let me share my screen. Okay. You scroll up. So he thinks that vision in general is probably at first it was just to tell the difference between whether it was day out or night out, right? So it is just a light detector. Probably plants have something like this, right? So it knows plants will move towards if you put it near a window and halfway in the light, so the light from the window can hit it, and halfway where the light's not getting to it, slowly the plant will grow towards the light by the cells on the side with the light will reproduce more, so it gets heavier, so it can tilt towards the light, right? So there's lots of reasons why it might be good to have, is it light out or is it not light out kind of detector. But eventually Marr thinks that when you talk about exactly the algorithm, the process that our vision follows when looking around the world, it starts at this he calls it the primal sketch. It's just this 2-dimensional sketch of patches of light and dark, edges of objects. So patches of light and dark in my vision, maybe it gives me some 2-dimensional geometrical information. There's a square, there's an edge, there's a maybe like I can see the kind of the ground in front of me. It's light because there's light reflecting off of it, and then there's a big pit, so it's dark, right? And I can see the edge, right? So at first it's just the brain is processing, the algorithm processes patches of light and dark, and then it moves on to assigning those patches of light and dark distances. It's still two-dimensional, but it's two-dimensional with like a little tag on it that says, roughly an arm's length away, right? It probably doesn't say 3 feet, 2 feet, right? It's probably, you can reach that tag. You'd have to walk a little bit to reach that tag, that's really far away tag, right? So it's not quite, I mean, one thing we want to understand in cognitive science is what are the distances that the visual system or the mind at this very primitive level uses? Because it's not 3 feet, 6 feet, 10 feet. It's some other like arm length. It would be a bit of a walk. It'd be a run, right? There's some way in which it tags things in our vision. So we've got a two-dimensional picture of patches of light and dark, and also tagged with how far they are. And notice that still, it's all from my perspective. Patches of light and dark from my perspective. Just patches of light and dark tagged with how far they are from my perspective. And then that's the 2.5 dimensional sketch, right? Because it's still two-dimensional, but it's like 2.5 because it's still the light, they're tagged with how far those patches are. And then the last sort of evolution in this process, in this algorithm, is it actually builds a 3D model. And this 3D model is not from my perspective, right? It's a 3D model from kind of the view from nowhere. So it takes those patches of light and dark with tags of distances, and now it builds a model of objects with surfaces, and it has me maybe located in this map, this 3D image, and I work with that. And at that point, it starts tagging things as objects, like that's a bucket, that's a hammer, that's me, right? So this is, I mean, all at the algorithmic level, but David Marr then goes on to try saying, how does this work at the implementation level, right? How does this 3-step process of building first a primal sketch, and then a 2.5 dimensional image, and then the full 3-dimensional image work? And he gives us this model, right? You can see particular parts of the brain, tasked with particular parts of this process of this algorithm. And even though, the intermediate step, which is building this 2.5 dimensional sketch, is building this 2-dimensional file, but like it's distributed across different parts of the brain, right? There's a part of the brain registering object trajectories, which direction it's going, size, representing motion, right? These are different parts of the brain that are wired up, located in different places, maybe close to each other, maybe far. And if there's damage to one, the other ones can operate fine. And so you get some weird results in people's behaviors and what they see. Yeah, so we get what is vision for at the computational level. We're not talking about color vision right now. Now we're just talking about vision in general. He says, to understand vision, we need to think of it as to build a 3-dimensional representation of our surroundings in order to identify objects. Algorithmically, how does it work? Well, first it builds this primal sketch. Then it builds this 2.5 dimensional model, which is patches of light and dark, but with, tagged with how far they are. And then lastly, it actually builds the final 3-dimensional object. Great, that's the computational level, that's the algorithmic level. And then at the neural level, at the level of implementation, physically, where in the brain does this happen? How many subcomponents, like how does it divide up these tasks? Well, here we've got a model of that, right? And you can study that by seeing what parts of the brain are firing when people are doing things. What sort of abilities do people lose when a certain part of their brain is damaged? Doing transcranial magnetic stimulation, where you put a magnet over a certain part of the brain that disables it, and you can see what they can do and they can't do, and then you kind of know, okay, that's what that part of the brain does. So great. I mean, what we're talking about this today is just this idea that cognitive science involves, understanding the mind at all of its levels. And David Marr's kind of influential way of doing cognitive science that was set forth in his account of vision where he tried to understand vision at what he called 3 different levels, what he called the computational level, right? Why do we have this ability? What is this ability? Why do we have it? What's its inputs and outputs? And usually the inputs are not enough to produce the outputs. So there's something else going on in the processing that adds assumptions or draws upon other information to help produce the outputs. Algorithmic level, exactly, what's the step-by-step procedure that the mind's using to go from these inputs to these outputs and to accomplish the purpose of this module. And then lastly, the implementation. How is this physically implemented in the brain? And then we understand how color vision works, how vision works, how three-dimensional understanding vision of the world works, how other things work, like depression, certain emotions, hatred, anger. How do I know what other people are thinking? How do I have my own thoughts? That's my alarm that I need to wrap things up. How do my reasoning abilities. We're going to talk later in the semester about reasoning being a product of social interaction. And you might think that reasoning evolved just so I could think through problems by myself and have a better view of the world. But we're going to see some evidence that really the reason it evolved was in order to convince other people to trust me and to communicate information with them, that I'm a stranger. If you're my family member, I might evolve just an automatic trust to believe what you're saying. But if you're a stranger, presumably we just distrust strangers. But maybe if they can give me an argument and explain to me why they're right, now I can trust them and I can cooperate with them and I can expand my circle of cooperation. So we're going to see that maybe reasoning was really a product of enabling social interaction as the reason for it. And then how does that affect, how it works on the algorithmic level and at the level of implementation. Great. So let me stop there. I'll stop sharing my screen. Are there any questions about this week's? I'll try to make this more interactive next week because some people will have submitted their questions ahead of time, and I'll try to not prepare as much content to talk about too. That might help. Okay, so let me stop recording because I want to tell you